We are live. Welcome, everyone. For this particular course, you will need to have some understanding of first year calculus. This head's not going to work. Our first year calculus at university. But if you are interested and you don't have that knowledge, that's completely fine as well. It's just that you may have to research certain terms in here. So I thought I'd start off with something very simple and build up to the Luxemburg norm. So what we can see firstly is the Pythagorean theorem, which you would have learned as a kid, hopefully. C squared equals A squared plus B squared. So what is the length of C? Well, you could see simply here that if that is C, and its relationship with A and B, you just have to square root both sides and you take the positive value, of course, and that will give you C. So C is the square root of A squared plus B squared. Okay, and you can see I've got it here for you. For example, 3 squared plus 4 squared equals 9 plus 16 equals 25. Take the square root, you get the length is 5, for example. Okay, so it's the length or magnitude of the vector. Now, what happens if we rewrite it this way? This is just to show what most of you will still know. We've got here that the norm, which is written like this, is just the square root of A squared plus B squared. Still simple, still high school mathematics. Okay. Now, let's say, for example, right, that we divide by the norm. If we divide by the norm, then of course we now just have that the left-hand side equals 1. So what are we now saying? We are saying that if we take our original triangle and we take the square root of A squared plus B squared and we divide that by the length, right, or the norm, we're going to end up with a norm of 1. So what we're doing is we're scaling down the triangle to the point where we are guaranteeing that this length here is 1. Okay. So let's keep going. Why do we want to do this? Well, we can then rewrite it even further and we can take it to look like this, right? And now let's now let's look at it this way. So you can rewrite it and you can say, well, what number, let's call it lambda, can I feed into the original system? So instead of A squared plus B squared, I can say A over lambda squared plus B over lambda squared equals 1. So now I've asked the question in a slightly different way. And it's like, well, why would I want to do that? Well, we'll come up to why in a sec, because we're going to look at how to look at some of these norms in very warped types of situations. Okay. So simply by asking the question in a different way, you can actually enhance the power of this type of theorem into a new version. Okay. Uh, Now we can rewrite this as A squared over lambda squared plus B squared over lambda squared equals 1. Okay, so we're saying to ourselves, what number can I feed back into this system which will scale down the original vectors so that their norm, or the norm, is 1. Okay. Now keep in mind that's what we're doing. Now it turns out this is a very simple scenario. In this case, lambda just equals the norm, which is the magnitude of C. Okay, which we already saw. If you divide by the length, you'll scale down the triangle down so that the hypotenuse becomes 1 in this particular case. Okay, why is this important? Now let's start generalizing. Okay, now we're going to start generalizing. So we're going to start looking at year 12 maths, maybe year 12 sort of advanced maths, which is still relatively simple for those who are postgraduates looking at Luxemburg norms. But just be a bit patient so that I can bring everyone else on board as much as possible, right? So now let's have a look at this, right? Let's say instead of saying A squared plus B squared equals C squared, now let's look at x1 squared plus x2 squared plus blah, 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 all the way up to xn squared equals lambda squared. What have we done? Well, we've turned the triangle into an n-dimensional triangle instead of a two-dimensional triangle. And this becomes hard, of course, to conceptualize, but mathematically you can actually write it down. Okay, what does that give us? Well, it gives us the distance, okay, which is the norm would be the magnitude, being the magnitude lambda, That would give us the distance or the hypotenuse in a multi-dimensional triangle. Okay. Now, why is this important? Once again, we're generalizing the norm. We're on our way to generalizing to a much higher sort of more broader sense of the definition of norm. Okay. So let's keep going. Now what we can do is imagine that instead of saying x1 squared plus x2 squared, imagine that x2 was so close to x1 that there was no gap between them. Is that even possible? Well, that's when you start getting continuous functions, right? And we've seen integrals. You would have seen integrals in year 11 and year 12, where you have a sum of points where each point can't really be cut off from the point next to it. I'm using layman's terms to help include as many people as possible. So let's say like 1 plus 1 point. Imagine you have 0.01 plus 0.011 plus 0.0111, and you sort of get this continuous line. So what happens in that case? Well, you end up getting the integral, right? So this is a very, very simplified layman's explanation. So we've now turned this thing up here into this thing here, which is that every single possible point where there are uncountably many points on this particular region from A to B, but it's still all of those squared gives you lambda squared. So we've turned it from a discrete variable into a continuous function. Okay, and so therefore the sum becomes an integral. And now we're looking at summing them all up. So this bizarre sort of uncountably infinite dimensional triangle. And you're thinking, why are we doing this? Well, why are we doing this? Because we can actually then restructure this in the same way that we did with the original norm, which is, let's ask a different question. What scalar can I plug into this x of t somewhere, divide by it to shrink it down such that the integral will equal 1? Okay. So we put lambda in there, and there it is. So lambda becomes our what we call a Luxemburg norm. It's the norm such that when you feed it into this system, you end up getting 1. This is not the complete definition, but we're slowly getting there. Why is this important? Okay, it's important because what happens if instead of squaring each x, x1, x2, x3, x4, all squared, all squared, all squared, all squared, what happens if some are squared, some are cubed, some to the fourth? Okay, so why should we necessarily say that they're always squared? Like if you look at this example, I'm not sure if you can see that. You might not be able to see that. Let me move my screen. So in this particular example, you can see that we've got a over x is lambda in this case, but it's not squared, squared, and squared like we had before. This is a cubed here, right? So in this particular case, let's just delete these to make it look a bit easier, right? Instead of a squared plus b squared is c squared, we've got a squared plus b cubed is c squared. Okay, and this is important because the application of this is for very advanced types of materials that follow these types of behaviors, right? So what happens is that it might very well be that we've got all these different powers for each of the different terms, but there are uncountably many terms, so you can represent that with uncountably many powers. That of course forms a continuous line P of t. So now we've got this thing where we've got what, you know, this something squared, something cubed, something four, something this. What's going on here? So we can't just square root the right hand side to get us back down to what the norm would be. So what do? We've got to feed the norm into the system from the beginning and say, what scalar do I put in here such that when I scale everything down, it doesn't matter which power each one goes to. They're going to follow this function P of t. And what happens, what do I have to scale it down by so that that integral becomes 1? Okay. And if that number exists, that number is the Luxemburg norm. Okay. And it's basically it's the infimum of this particular number. So that number, you might not reach the infimum, but it doesn't actually matter for this particular explanation. All right, so how can I explain it to you? Well, let's go back to simple scaling, right? This would be x to the t squared, and then you square root it to end up getting this here, right? And this particular point here would have been the c square root of c squared in our original a squared plus b squared. But now we've got an infinite amount of a squared plus b squared plus c squared, and it's in a continuous form where a is so close to b that in fact you can't even slice the two apart. And so you end up getting that continuous line. So we've got here, that's very easy. You can just square root the whole thing, but you can't do that with a Luxemburg norm because each one of these little xt's has a different exponent. So there's a pt. So you can't take the 1 over pt root. It doesn't make sense because we are integrating with respect to t. You can't take t outside for those of you who studied calculus or p of t outside. So what do you actually do? You've somehow got to get the scalar before you calculate the integral. Okay, and this is an example of why you can't do it, or you can do it in this case because when you have alpha x as the length, well, that's the same as having alpha in here, and you can take the alpha outside the integral. Okay, but you can't do that with these. This here you can't actually do 1 over pt because we are trying to figure out what's going on with respect to t. So you can't take t outside. You've got to figure out what's happening first before you can actually reverse the function. In other words, to try and get this norm, you can't do that. Okay, so it's fundamentally flawed, as I was saying. Right? So we come to this now. That's here. We've got the Luxemburg norm is lambda greater than 0, but the smallest one, and it's the infimum of that. If you studied infimums, you might have done that in real analysis at university. Okay, so let's have a look at a concrete example. You can see here that if we double the norm when all the exponents are the same, then you're going to get double the norm either way. So if you double the a squared plus b squared, etc., before calculating the norm, or if you double the norm afterwards, you're going to get the same answer, right? But you can't do that with a variable exponent. And that's because, for example, look at this. We started with 2, let's just say 2 squared plus 3 squared, right? Equals c squared, right? Which is what, 13, root 13, let's just say, right? But you can't double because if you put the 2 in there, you've got 2 squared and then you've got 2 cubed. So you're starting to get a warping of that scalar, that 2, which is doubling everything. But the doubling is not working because at some point that double component goes to 1 power and then at another component it goes to a different power. So you're warping this scalar. So you can't actually do it that way, right? So therefore, that's why if you notice here, you'll end up, look, I'm going to skip this because there's no one here anyway. Let's just do a summary here, right, of what we were saying, right? What do we got? Finding the scalar factor. Yeah, this was my entire summary that I did earlier, but there's no one here, so I won't bother you with that. Luxemburg norm. Okay, and scenario, we've got a consonant exponent. This is quite easy because the norm is just the nth root of the sum of each of these terms, right? So like a squared plus b squared is c squared, all you have to do is just take the square root of c squared, right? You can't do that when it comes to when each power is different, right? Because you've got here, for example, this a over lambda is to one exponent, p1, and then b over lambda is to an exponent, p2, right? So if you took lambda out, you'd end up with lambda to the p1 plus lambda to the p2. And I'll show you here what actually happens, right? If you look at, let's just say x is lambda, what actually happens here is that you end up getting, to solve for x, you've got a polynomial which may or may not have roots that you can calculate. Okay. Whereas if this was also squared up here, then all you would have to do is notice that x is just on one side. So you can just basically divide both sides by c squared and then square root the x squared, and you end up getting that x, which is lambda in this particular case. Right? To make it easier for you, I'll actually put lambda in here. And there it is. Okay, that makes it a bit easier. So you can see we've got a polynomial. It's quite easy. You just have to put c over here underneath a squared plus b squared, and square root of lambda squared will give you lambda. But as we were saying, let's just change that to the power of 4. So now we've got a over lambda squared plus b over lambda to the fourth equals c squared. And we now have very complicated versions of what lambda looks like, as you can tell. Okay, so and the polynomial that it has to satisfy is this one here. Okay, so as once these functions become, instead of having 2 and 4, which are discrete variables, imagine if you had a continuous line of all these different powers, you're going to end up having a very bizarre, infinitely long polynomial of which lambda would be a root. And that becomes quite difficult. So that's why we look at the Luxemburg norm. I hope I've explained it in some form that is easy to understand, but I will talk to you later.